is downloaded from the unit, it's still not in what we call engineering units. And what we do is we convert that data now into the various parameters that are recorded. For instance, altitude, heading, airspeed, and a host of other parameters. The minimum is 88 parameters, but almost all of your modern aircraft now well exceed that into several hundred parameters.
What is several hundred? 200, 800? What would you think?
It really depends on the aircraft. They can exceed 1,000.
What about 11-year-old 777?
Yeah, I'd have to look. I'd have to look what that is, but I can't speak to that directly now. So what Erin does here is she gets the data and begins to go through the algorithms to do that conversion. And each box and each aircraft has its own configuration. And we have files on all of these types of aircraft. We either get them from other AIBs or from the manufacturer or from the operator. It depends on where the most current and complete information is. And in fact, behind you is a lot of the manuals for those sorts of things. We have a lot of it electronic as well. That's just the older stuff. We keep a complete catalog of it. So once she gets it here and does that conversion, it's going to be able to be read out by our investigators and the investigative team. And we do that in a software that we developed, and it's an acronym spelled like the word CIDER, C-I-D-E-R. Okay, that's our software that reads these data out and creates the plots. So what Erin will start doing is in our group process of investigation, we'll have party members come in, technical specialists from each of the parties that can help us and assist us in validating these data sets. And that's the primary goal. Again, like I said, we're going to try to do this within 24 hours. We want to validate the data, and we want to get the most crucial parameters plotted up and out to the investigators so they can start working on the most vital aspects of the accident on scene. So I'll turn it over to Erin. She's going to give you just some examples, some screenshots of what we do. You'll see the binary data on the left, then convert it to engineering units, and then we also have the ability to generate a real-time animation for our purposes only that helps us to validate and understand the data. When you see a bunch of traces, sometimes you want to see what's happening all at the same time in a more visual presentation, and so we're able to make an animation. Now this is just an example. This is one of the ones we went to full production with, but we also have the ability to animate the aircraft itself. The example we're going to give you here and then in the next room is what's commonly known as the Miracle on the Hudson. So it's just, I'm just trying to give you an example. That's a water recovery transport aircraft that we did. So Erin, why don't you take it away?
So once we download that file over in the other room, we will transmit it through the network over to this system. We'll have a group, a flight data recorder group and a cockpit voice recorder group. NTSB person is the group chairman, but we have people who are represented in the investigation. So there'll be somebody from the manufacturer, somebody from the operator, etc., that will be represented on that group. The reason is every single aircraft is very different. A lot of what we're doing here is systems and trying to validate parameters, so we need someone who can get to the answer. We get information from the manufacturer of the aircraft that has a data map, and that data map translates all the zeros and ones into actual parameters. The original flight recorders were 5 parameters. Nowadays, aircraft are being delivered with thousands of different parameters on there. So they measure all the different systems, the various airspeed indicators, but they'll measure all of the airspeed that are on there instead of just one side or the other, which is what the original designs were. So we want to get, this is an example of the download file that I did. This is an example of what it really looks like. All it is a serial data stream, so it's zeros and ones. We need to map all of these zeros and ones into how high, how fast, etc. We cannot do that unless we have the information from the aircraft manufacturer. So they'll provide it in a software program or in a document, and it'll tell us basically an address system. So each of these is into blocks that are different airing standards. Each of these 12 bits, for instance, might represent airspeed. Each of these blocks that are dark and light will represent 1 second of data. So when you have a recorder that may not have stopped the way it normally does, you might have some corrupted or invalidated data at the end of it. So you have to make sure, kind of like closing out a CD, you have to make sure that the program understands that there is some data there. So that's why we get down to the bit level. From the data map perspective, we use an example of the individual parameters. So we'll figure out which one of these words will map this word back to a parameter, and we'll do the engineering conversion. And what that is depending on the different sensor on the aircraft that it's picking it up, it'll be a various equation to get it back to how many G's it was. So that's what this information is in here. There are standard maps for modern aircraft that are coming off, but the operator a lot of times has the ability to modify that if they want to for the various information that they're looking to capture or the rate they want to capture it at. But there is an FAA standard or regulatory standards that they have to abide by for minimum number of parameters and sample rates, etc. So we'll put the equations in here, and the next part of what we do, which is what the group really helps us out, is actually validating the data. You need someone, in this example, it was an A320. It's very helpful to go through and figure out, get the performance numbers to figure out what is an A320 supposed to rotate at, etc., so that we validate that information. So this is after a lot of work, we come up with an engineering plot, and we will put plots together depending on the information we're getting back from on scene, on the field, and what we know about it from ATC and various other sources.
Are you able right now to put that plot on that screen?
Let's see. Okay.
So that's a typical plot that we'll be generating and working with, and that's ultimately what we're trying to do, is validate that data and get that data out to the field.
What are the lines mean?
Okay, so these are, yeah. Aaron, just use the mouse pointer there and maybe take them through one or two of the parameters. So this is a time history of data. Okay, time is on your so-called x-axis, going along horizontally. And each of the colors associated with a different parameter. And if you find the color, the scale associated on the left or right side of the plot, it'll give you the scale associated with that particular plot. Okay, so it's like putting a bunch of individual plots all on one plot. And that's important because a lot of times we want to compare one to the other. What's the airplane doing in pitch at this particular airspeed, for instance? And that's what we're trying to do. And then Erin will go through that with her group, validate things, and identify certain events or certain issues. In particular with the data, you see, excuse me, there's an issue of the discontinuity of the data and that sort of thing. We point those things out to the group.
Is that, when you have a discontinuity like that, is that just a fraction of a second, or can you tell us how you arrived at whatever's between the two discontinuities?
Well, it varies widely. Erin can give you some details on that.
It depends. I mean, if there's any sort of a power interruption to the main source of power, it may be a fraction of a second. Like I said, with those zeros and ones, you can generally go into the zeros and ones and see that. You'll be able to see that there'll be some sort of an interruption or a corrupt period in there. It could be a couple of seconds. It really depends on what the event is. But generally, you'll see a break in data or the numbers. You have each of these blocks has an assigned number. If you start skipping numbers, then you know you've got what we call an out of sync situation, that it's lost its sync somehow.
So, maybe I missed this, but so what would cause that to happen?
A power interruption.
In this case, what was it, the bird strike or something? Or?
They did have an engine power interruption, but it may be a bus switching. I'd have to look in this particular. Each airplane goes off of different buses. The flight recorders will be off of different buses. So if you have a bus switch, or if there's a power interruption, or even the source of data that's coming in if that gets interrupted. So you may lose some parameters, but not other parameters.
So is that area of the grid there, is that where you look for, okay, this is where the trouble happened, or?
Well, in this case, I mean, what we're looking for is normal operations. When we see a break in normal operations, so when you're on climb out, so this is altitude, and this is airspeed, so you have altitude, so this is an aircraft that we know is taking off. If you lose all of your engine thrust during takeoff, that's a problem area for us. So what we'll do is we'll concentrate around that area. So we rely on information, obviously, from that we've gotten in, but then we also are also looking at things in the data that may have caused that to happen. So there may be events back here like master warnings, cautions, etc.
Another important aspect of what's done here is we start to time correlate everything, not only the FDR, but the CVR and the radar data and that sort of thing to make sure we have the most complete picture possible. I have members of our staff here, and that would be representative of the various party group members. And what they'll be doing is Aaron will be playing back the recording so that they can listen to it, and then they begin to transcribe basically one sentence at a time all the way through the CVR. And we have specialized software that helps us do that, where we can look at the waveforms, and a lot of times in this process, as Aaron will explain, you go back and forth over the same words over and over and over to make sure you have it correct and that you have the timing associated with that correct. So Aaron, if you could go ahead and explain the specifics.
Sure, so it's a similar process with the group chairman and obviously the different parties. There are 30-minute recordings and 2-hour recordings. We'll generally, once we get the file in here, we'll go through the entire 2 hours first to listen to the entire thing, and then we'll start the transcription process. There's 4 different channels: the captain, the co-pilot, the cockpit area microphone or CAM, and a 4th interphone channel. So generally one of the people from the party can identify the voices for the cockpit people speaking, the co-pilot or the captain. And once we start the transcription process, depending on the channel and who says what, we will attribute that to the person. So hot 1 would be the captain's microphone, hot microphone. The CAM is the cockpit area microphone. We'll also designate if some of the audio comes from a different device like a EgyptWiz. You'll hear things in the background that will be making calls, and we'll attribute those to an EgyptWiz. We also put radio transmissions in there, and generally we'll put departure or a radio transmission from the cockpit. So again, 1 is captain and 2 would be the first officer. So you can see here, this is basically a visualization of audio. So through our headsets, we're actually listening to the audio, but you have an elapsed time down here on the bottom, and these are the various channels. So you'll hear, the ATC on one channel, maybe on the CAM, and it'll come through on the other channels, and sometimes you'll just have the one person talking. We can also visualize this differently. So a lot of times we're listening for sounds in the background, or if we're listening to alerts, etc. We will try to filter or enhance the sounds when we're trying to focus on something. We do put the actual text, so the purpose of the group is to try to transcribe as factually as possible, and we try to come to a consensus.
So you're basically all listening to the same thing. Do you hear this? Do you hear this? And it's,
Yes.
if you have disagreement, you go through it again and again
Yes.
until you all say, he said, she said, whatever.
Yes, we try to come to a consensus, and normally we do. It does, there's a lot of background noise, especially when something's going wrong, so we will sometimes just take a break. When you're listening to it over and over and over again, it can get very tiring. We'll take a break, start over again in the morning, and then it will become more clear.
Is it, I think Joe mentioned something about when people aren't speaking, there's still sounds you can hear in the cockpit. Well, can you give us a sense of that?
Sounds similar to seat moving, sounds similar to door opening, sounds similar to door chime.
In other of the sounds, for instance, there'll be background noise, and you can actually, through spectrum analysis, do things like analyze engine RPM from that sound, for instance, or a gearbox RPM, or even you can derive, let's say, a speed or something from tires rolling down the runway. So there's a lot you can do on the spectral side of the analysis of the audio file as well.
Even if somebody's not speaking.
Yes.
Aaron, is it, I would think this can be emotionally taxing to listen to these kinds of phone calls. Let me skip these. Phone calls. I would think that this can be emotionally taxing to listen to this kind of a conversation.
I always relate it to what trauma surgeons must go through. Is you're there trying to get the job done, so you separate yourself from it. I mean, you're trying to make aviation safer is what the bottom line is. So that's my personal philosophy. I can't speak for anybody else, but you know, we want to make sure this never happens again. So it's something that we know once we get to the bottom of it and give this tool. This is only one of many other parts of the investigation, but we know that it'll provide some information to the rest of the investigative team.
Having read a few of these, occasionally you do write unintelligible, yes?
Yes, it is very difficult to hear sometimes. There's a lot, like I said, the ambient noise, especially in the older airplanes, because of just the microphones aren't as good. They were not wearing hot microphones. It's very, very difficult, and sometimes we're not gonna, you know, create something. If nobody can understand it, we put unintelligible. I mean, we just can't hear it. There's a lot of colloquialisms that happen. I mean, when, you know, somebody's pointing at something, you can't hear that. So they might say, wow, that doesn't look right. No, it doesn't. But you don't know what they're talking about.
And just how many people listen at one time? Generally, you said you start out with a group of 3, right?
That's
and you
right.
expand out to,
And then we'll expand out usually to, say, a group that could consist of, say, 6 or 8 folks.
What happens if this is, you know, do you bring in a native speaker if the pilot is not a native English speaker?
Right, we've handled that in a variety of ways. You know, we can get folks from here that might speak the language, our own staff, folks from, say, the operator who can help us with that, or even we've worked with our State Department to provide an